Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. So, we were discussing about the turbine flow, say the theory, and then we were discussing the solution of turbine problems, especially to determine the velocity distribution by the first model zero equation models. So, the last time we have seen the turbine flow over a flat plate including smooth type and rough type flat plate. So, now or rough surfaces and smooth surfaces we have seen. So, now here in today's lecture we will discuss mainly the turbine flow in pipes. So, say the most of the theories which we have seen for the turbine flow over flat plate or smooth surface or rough surfaces are very much applicable in a very similar way we are trying to utilize for this turbine flow through pipes also. So, here you can see now say we are discussing now the velocity, say our aim is say here the pipe is there and flow is turbulent. So, we want to determine the mainly the velocity distribution for the turbulent flow through the pipe. So, we are considering a pipe of diameter d and then say we are considering length L and then we want to determine the at any cross section we want to determine the velocity distribution. So, as far as a pipe is concerned, as I mentioned earlier, for the normal surface can be either smooth or rough. So, similar way here also the pipe is concerned we have to consider the pipes as a smooth pipe or a rough pipe. So, like say for example, say PVC pipe or that variety of pipe, say depending upon the roughness we will be considering as smooth and hydrodynamically we will be considering as smooth, or we will consider sometimes like say concrete pipe as a rough pipe. So, say the theory which we will be discussing here for smooth pipe and rough pipe, there are slight variations. So, that is why we are classifying here the pipe as smooth pipe, smooth boundary pipe type and rough boundary type. So, here in this slide you can see for smooth boundary, even though it is not perfectly smooth, you can see that there are small say projections like this, but in comparison with the rough boundary you can see that for this rough boundary case the projections or the roughness is too much. So, we classify this as rough boundary type pipe and the first one as smooth boundary pipe. So, both will be considered. We will discuss with respect to the turbine flow theories, we will be discussing both case. So, first case is the velocity distribution of for turbine flow in smooth pipe. So, we have already seen the say the zero equation model or the with respect to the Prandtl mixing theory which we have discussed earlier. So, we have seen say how to develop the equation for the velocity distribution with respect to parallel flow. So, in a very similar way, say here as seen earlier, the velocity distribution for turbulent flow within fixed boundaries, example circular pipe, or flow past fixed boundary in the case of boundary flow along a flat plate we have seen earlier. So, may follow either power law or logarithmic law. So, we have seen the velocity distribution is concerned. So, either depending upon the case, the velocity distribution may be following say power law or logarithmic law. So, with respect to the power law, we have seen earlier the generally we can use this kinds of expression like the velocity at any location ux by u star o is equal to c into y into u star o by nu to the power n. So, this is the power law. So, here c and n are constant. U star o is the shear velocity and nu is the kinematic viscosity. So, now if c and n are not, then we can determine the velocity at any height. So, this is coming from the power law, and then as far as logarithmic law is concerned, we have seen this equation ux by u star is equal to 1 by kappa log e u star o y by nu minus log e beta. So, this equation also we have seen which is based upon the Karman's and Prandtl's approach. So, one is based upon the power law, other one is logarithmic law. So, now what we have seen earlier with respect to flow over a flat plate. So, now we are trying to apply very similar way to the pipe flow by using the same concepts. So, here now for the by using the power law, say there is one equation, and using the logarithmic law there is another equation, and also Nikodas has conducted large number of experiments as far as turbulent flow in pipes are concerned, and then he has also derived a certain expression for velocity distribution in pipe. So, as per Nikodas, he has through his experiments he has shown that ux by u max, that means the velocity at any location divided by the maximum velocity is equal to, can be expressed as y by r, where r is the radius of the pipe, to the power 1 by n. So, this n is a constant which can vary depending upon the Reynolds number from 6 to 10, and Nikodas showed that this is valid between the Reynolds number 4000 to say to the, here you can see about 3.2 million up to this level 4000 to this 3.2 million Reynolds number, it is valid. So, that is his experimental observation. So, if you consider the mean velocity with respect to the Nikolas experiment, here he has shown that with respect to the mean velocity v by u max, v is the mean velocity in the pipe, and u max is the maximum velocity in the pipe. He also derived an expression 2n square by n plus 1 into 2n plus 1 as shown in this equation number 4. So, this is done by Nikodas. So, these are the experimental observation. So, now based upon the power law and the logarithmic law which we discussed earlier, so we are trying to derive some expressions for first for the smooth boundaries, and then for the rough type pipes. So, here the velocity distribution in this slide you can see for smooth pipe, you can see that the variation, as we have seen the case of smooth pipe, the boundary is smooth compared to the rough type. So, the velocity variation is also very smooth, but like this as plotted in this figure. So, this will be more clear when we derive the real expression. So, now we have also seen earlier from the relation for velocity distribution using power law and logarithmic law, that is what we are trying to derive now. So, earlier Blasius has derived an expression for the friction factor F is equal to, he has shown that for turbulent flow in pipes, friction factor is equal to 0.316 divided by Reynolds number to the power 1 by 4. So, where F is the friction factor, and we can show this relation is corresponding to the 1 by 7th power law. So, now our aim is either by using power law or the logarithmic law, we want to derive the velocity distribution expression for turbulent flow in smooth pipe. So, now if you consider the boundary shear stress, so tau 0 is equal to F rho v square by 8, where rho is the density of the fluid, F is the friction factor, V is the average velocity. So, now this is equal to 0. So, now if you substitute for F here, so it is equal to 0.316 divided by R e to the power 1 by 4 into rho v square by 8. So, that is equal to 0.316 divided by, so this Reynolds number we can express as Vd by nu. So, Vd by nu to the power 1 by 4 into rho V square by 8. So, now if you substitute for diameter d is equal to 2r, and then we will be trying to approximate, we will be simplifying the equation. So, tau 0 is equal to 0.316 divided by 8 into 2 to the power 1 by 4 into rho into V, say nu to the power 1 by 4 into V to the power 7 by 4 divided by r to the power 1 by 4 as shown in this slide. So, here you can see in this slide the expression for tau 0. So, after simplification of this, we get tau 0 is equal to 0.033 rho into nu to the power 1 by 4 into V to the power 7 by 4 divided by r to the power 1 by 4, where r is the radius of the pipe. But now we know that the shear stress at the boundary tau 0 is equal to rho into u star o square. U star o is the shear velocity. So, if we use this relationship here, so that we can write u star o square is equal to 0.033 into nu to the power 1 by 4 V to the power 7 by 4 divided by r to the power 1 by 4. So, this we can now simplify as V by u star o to the power 7 by 4 is equal to 1 by 0.033 into u star o into r by nu to the power 1 by 4. So, or we can write V by u star o is equal to 6.99 into u star o into r by nu to the power 1 by 7. So, this expression we are getting from the power law as given in this equation number 5. So, as we have seen, say if you use, say for the power law, n is the constant which is varying from 6 to 10 as we have seen. So, now if you use here for a particular case, say n is equal to 7, then we can see that, and the mean velocity V and maximum velocity, generally for pipe flow we can write, we can approximate the average velocity V is equal to 0.8 times the maximum velocity or 80% of the maximum velocity. So, if we use this approximation, n is equal to 7 and u max, the V is equal to u max, then as shown in this slide, you can write equation 5 becomes u max by u star o is equal to 8.74 into u star o into r by nu to the power 1 by 7. So, this is equation number 6 here as shown in this slide. So, now you can see that this is, as I mentioned earlier. So, this is coming from the 1 by 7 the power law. So, now the velocity at any point. So, here we derived for the maximum, say at the with respect to center point. So, now that is for r. So, now if you substitute r with respect to y any distance from the pipe wall. So, here you can see that, say ux by u star o is equal to 8.74 into u star o into y by nu to the power 1 by 7. So, this is the equation number 7. This is the expression with respect to the power law. So, here it is shown that we can experimentally show this expression is valid well up to Reynolds number 100,000 and beyond 100,000. So, earlier we have seen the with respect to Nukoda's experiment we have shown this expression, but now when we realistically measure very accurately, then we can see that this with respect to power law we can get the expression up to generally up to a Reynolds number of 100,000, but up to that only generally the power law can be applied, but beyond that we have to go for the logarithmic law which we have seen earlier. So, equation 7 here in this slide you can see equation 7 agrees well up to Reynolds number 100,000, and beyond this 100,000 experimental measurement shows that we have to go for the velocity distribution by the power logarithmic law. So, here as we have seen the logarithmic law is given ux by u star o is equal to 1 by kappa log e u star o into y by nu minus log e beta. So, now we have already derived an expression for based upon the power law which is as in equation number 7. So, now but various measurements in reality shows that this is valid, this equation is valid generally up to a Reynolds number of 100,000. So, we say it is observed that beyond 100,000 we have to go for the logarithmic law. So, for this turbulent flow through smooth pipe, so now we will see how to derive an expression based upon the logarithmic law. So, now the logarithmic laws we have seen earlier, ux by u star o is equal to 1 by kappa log e u star o into y by nu minus log e beta. So, now again the experimental investigation made by Nicola suggests that the velocity distribution is given by ux by u star o is equal to 2.5 log e u star o in y by nu plus 5.5. So, here you can see with respect to this experiment and the logarithmic law, we can see with respect to the Nicolas experiment. So, here the constant here is 5.5, or in the previous expression kappa is equal to 0.4 and beta is equal to 0.11. So, now in terms of normal logarithm, this equation 8 can be expressed as ux by u star o is equal to 5.75 log 10 u star o into y by nu plus 5.5. So, this is the expression for say turbulent flow in smooth pipe. Say here you see that the constants say determined based upon some of the experimental measurement by Nicolas. So, equation number 9 is valid for turbulent flow in smooth pipes at higher Reynolds number, for which the shear stress due to dynamic viscosity mu is negligible. So, this equation number 9 is valid for higher Reynolds number regime for turbulent flow in pipes. So, now you can see that, but as we have observed near the boundary generally a laminar sublayer occurs, and then this logarithmic law, this is not applicable there. So, there near the very near the boundary we have to use this ux by u 0 is equal to u star o into y by nu as given in equation number 10, and then some of the measurement by Richards indicates that for u star o into y by nu less than 5, the velocity distribution is given by this equation number 10, whereas u star o into y by nu is greater than 70, the velocity is given by previous expression, the logarithmic law, equation number 9. So, here again as per the measurement by Richards for various experiments for turbulent flow in smooth pipe. So, he has shown that whenever this expression u star o into y by nu is less than 5, we can use this very near the boundary, this expression equation number 10 can be used, but beyond that where this value is u star o into y by nu is greater than 70, we have to use the logarithmic law, and between this 5 and 70 it is actually say we have to, there cannot be a general law, cannot, is very difficult to derive. So, for u star o into y by nu between 5 and 70, the total shear stress consists of contribution due to dynamic viscosity mu and due to turbulent velocity fluctuation. So, it is very difficult to say put an expression, give an expression for this between 5 and 70. So, this is as far as very near the boundary is concerned. And now we can just if we use the velocity defect law. So, with respect to the earlier say the expressions, so we can write the velocity defect law as u max minus u x divided by u star o is equal to 1 by kappa log e r by y. So, now if we use this, so here you can see that if you use kappa is equal to 0.4, this is again u max minus u x divided by u star o is equal to 2.5 log e r by y, or this can be written as u x minus u max by u star o is equal to 2.5 log e y by r as written in equation number 11. So, this is coming from the velocity defect law. So, now to find out say the mean velocity distribution, we can use the earlier equation number 8, this equation number 8. So, if we use this equation, we can write u x is equal to u star o into 2.5 log u star o by y by nu plus 5.5. So, the discharge through the pipe, we can integrate q is equal to integral 0 to r, the r is the radius of the pipe, u x into 2 pi y dy. So, that is equal to integral 0 to r u star o into 2.5. If you use this expression here, u x u star o into 2.5 log u star o into r minus y by nu plus 5.5 into 2 pi y dy. So, here you see that the y is measured from the center. So, that is why the expression is written like this. So, once you integrate, we can get an expression for the discharge through the pipe as pi r square u star O into 5.75 log 10 u star O into r by nu plus 1.75 after integration. So, then the mean velocity, once the discharge is known, we can determine the mean velocity. Mean velocity is equal to the discharge divided by the area of cross section. So, here V is equal to u star O into 5.75 log 10 u star O into r by nu plus 1.75. This we can write in this form: V by u star O is equal to 5.75 log 10 u star O r by nu plus 1.75 as in equation number 12. So, now say again this equation number 12, you can see here, this is with respect to mean velocity, equation number 12, and here in equation number 9 is the velocity at any location. So, again we can get a velocity defect law for turbulent flow in smooth pipe as u x minus v by u star O is equal to 5.75 log 10 y by r plus 3.75 as given in equation number 13. So, this is the velocity defect law for turbulent flow in smooth pipe. So, now you can see that in most of the pipes the friction factor is a major component. So, now the friction factor F and shear stress we can relate tau 0 is equal to F rho v square by 8, where v is the average velocity of flow, F is the friction factor, rho is the mass density. So, now by using this also we know that tau 0 is equal to rho into u star O square. So, hence we can write the friction factor F is equal to 8 into u star O by v all square. So, now if you this tau 0 is here and then we are using this tau 0 again rho u star O square. So, both we use F is equal to 8 into u star O by v all square as in equation number 15. So, now in terms of Reynolds number we can write u star O into r by nu is equal to u star O by nu into v d by v into half. So, this is equal to r is into square root of f by 4 square root of 2. So, after substituting back we can write v by u star O is equal to 5.75 log 10 r e root f divided by 4 root 2 plus 1.75. So, that gives, that is equal to v by u star O is equal to 5.75 log 10 r e root f minus 2.577 as in equation number 16, or we can write f is equal to 8 divided by 5.75 log 10 r e root of minus 2.577 all square. So, or from this again we can write 1 by root f is equal to 2.035 log 10 r e root of minus 0.91 as in equation number 17. So, this equation number 17 is 1 by root of this equation. So, now this equation 17 is same, almost same as what Nicolas got. So, here a line passing through the various experimental points has however slightly different constant. So, Nicolas say with respect to his experiment he has shown this even the we got here 1 by root of is equal to 2.035 log 10 r e root of minus 0.91, but with respect to Nicolas experiments he could get 1 by root of is equal to log 10 r e root of minus 0.8 as in equation number 18. So, here this equation number 18 written here, this equation is called Prandtl-Karman law of friction for smooth pipe. So, here we can see that the friction is now, pipe friction is connected with respect to only the Reynolds number. So, this equation is called the Prandtl-Karman law of friction for smooth pipe. So, this is based upon the logarithmic velocity law as described in the previous slides. So, now here you can see the velocity distribution. So, for smooth pipe if you plot here as shown in this figure. So, here on y axis it is u by u star and on x axis it is u star o y by nu. So, if you plot this you can see say with respect to the various range of experimental data. First say for the viscous wall layer you can see that the variation is going like this, and then for the turbulent zone the variation is with respect to this. Here you can see u by u star 5 this with respect to this equation which we have seen. So, the variation with respect to u by u star and u star y by nu e can be expressed like in this plot here. So, this is u by u star with respect to equal to 5.5 plus 1 by kappa natural log u star y by nu. So, this is with respect to logarithmic law in the turbulent zone, and here with respect to the viscous wall layer you can see that u by u star is equal to u star y by nu. That variation we can, some places we can approximate like with respect to power law, or sometimes even linear variation can be for some range we can use, and then the turbulent regime we can use the logarithmic law. So, this is about the velocity distribution for flow in smooth pipe. So, now here for smooth pipe we have to find out the velocity variation, we have basically used the power law and the logarithmic law, and then we had made some comparison with respect to the Nikoda's measured or experiments, and then its corresponding say expression which Nikodas has derived, and then it is almost coming very nearby. So, that we can rely upon this kinds of expression for velocity for turbulent flow through smooth pipes. So, now here we will discuss the turbulent flow through rough pipe. So, here rough pipe is concerned, the velocity distribution at high Reynolds number is again here we use the logarithmic variation, logarithmic distribution. So, u x by u star o is equal to 1 by kappa log e y by epsilon minus log e alpha as in equation number 19, where epsilon is the roughness and kappa and alpha are constants. So, where kappa is the Karman constant, kappa is equal to 0.4, and as we have seen this b, if you use this b is equal to minus 2.5 log e alpha with respect to this expression, then we can write u x by u star o is equal to 2.5 log e y by epsilon plus b as in equation number 20. So, this gives the velocity distribution of turbulent flow through rough pipe. So, here the major difference you can observe here is we are put a term for the epsilon, which is the reference height with respect to the rough pipe. So, now this constant here, as we have seen, this constant b has different values for different regime, as we have already seen whether the pipe is rough, smooth or between which range. So, the value of b changes. So, for complete rough flow regime we can show that b is equal to 8.5. So, that we can write u x by u star o is equal to 5.75 log 10 y by epsilon plus 8.5 as in equation number 21. And then for hydrodynamically smooth pipe, as we have already derived in the previous slides, we can write u x by u star o is equal to 5.75 log 10 u star o into y by nu plus 5.5 as in equation number 22. So, now if you compare this expression with respect to the for the rough pipe as in equation number 20 and equating 20 and 22, then you can see that this b here, this b, if you equate b is equal to 5.75 log 10 u star o into epsilon by nu plus 5.5. So, for maximum velocity in a rough pipe we can write u max by u star o is equal to 5.75 log 10 r by epsilon plus 8.5 as in equation number 23. And now, if you subtract this 21 from 23 and rearrange the terms as we got earlier, here again we can get a law called velocity defect law. So, as this velocity defect law, the importance is, since generally for pipe flow the maximum velocity is either known or you can easily determine. So, that with respect to that we can determine the velocity variation at various locations. So, the velocity defect law now become u x minus u max divided by u star o is equal to 5.75 and log 10 y by r as given in equation number 24. And very similar way what we have done for mean velocity. So, here again if we assume mean velocity v is equal to 0.8 u max, and then if we put q is equal to integral 0 to r u x 2 pi y dy and v is equal to Q by A. So, we can change this equation for rough pipe as V by U star O is equal to 5.75 log 10 R by epsilon plus 4.75 as in equation number 25. So, this is a relationship with respect to the mean velocity and the shear velocity and the radius of pipe and epsilon as in equation number 25. So, now this equation number 25 as in this slide, we can again deduct this subtract this 25 from this equation number 21. So, that we get again a velocity defect law based upon the mean velocity. So, earlier velocity defect law which we have seen is with respect to maximum velocity. So, here we can derive a velocity defect law with respect to the mean velocity. So, we can write u x minus v by u star O is equal to 5.75 log 10 y by r plus 3.75 as in equation number 26. So, this equation number 26 is called universal velocity law or velocity defect law, since u x minus v is considered, or it is also called Karman-Prandtl law for velocity distribution in a circular pipe. So, this is one of the generally used equation for turbulent flow in rough pipe as say expressed in with respect to equation number 26, which is the universal velocity law. So, here this friction factor for turbulent flow in rough pipe, again we can with respect to F we can write F is equal to 8 u star O by V all square. So, u star O by V is equal to square root of F by 8. So, that here for this u star O by V with respect to this expression we can substitute back. So, substituting for V by u star O in equation number 25, we can get 5.75 log 10 R by epsilon plus 4.75 is equal to square root of 8 by F. So, if you simplify this, we can get 1 by root F is equal to 2.03 log 10 R by epsilon plus 1.68 as in equation number 27. So, here again we are getting an expression with respect to the radius of the pipe and then with respect to the friction factor and the reference height epsilon. So, that is the relevance of this equation number 27. And again for rough pipe also, turbulent flow in rough pipe, Nikodas conducted large number of experiments and he has also derived an expression. So, here in comparison with Nikodas experiments, equation 27 can be written after approximation of the constant as 1 by root f is equal to 2 log 10 r by epsilon plus 1.74. So, here you can see with respect to the measurement by Nikodas, again small variation is there. So, this is the expression equation number 28 is what is generally used. So, since now say, but it is almost very near to what we are getting with respect to the theoretical development here. So, now here this equation number 28 is called Prandtl-Karman's equation for turbulent flow in completely rough pipe. So, this expression equation number 28 is called Prandtl-Karman equation for turbulent flow in completely rough pipe. So, now we have seen the various expression for velocity variation for turbulent flow in smooth pipe and turbulent flow in rough pipe. So, but say we have to define which pipe is smooth or which pipe is hydrodynamically smooth or which pipe is hydrodynamically rough. So, this we can use say some expression here. So, we say that a pipe is said to be hydrodynamically smooth if u star O into epsilon s by nu is less than 5, where epsilon s is the equivalent reference height and u star O is the shear velocity. So, whenever this expression is less than 5, we call the pipe as hydrodynamically smooth, and then if this expression u star O into epsilon s is x by nu is greater than 70, then we call the pipe as completely rough. So, accordingly we can use the, depending upon whether it is smooth pipe or it is rough pipe, we can use the corresponding expression for the to find out the velocity variation in for turbulent flow in smooth or rough pipe. And then between 5 and 70 of this U star O by into epsilon by nu. So, here when it is between 5 and 70, we say it is a transition between the smooth to rough. So, here it is very difficult to get an expression like what we have derived for smooth or rough. So, either depending upon the value, we have to use either one for the equation for rough or smooth depending upon the case. So, that way we can see whether the pipe is hydrodynamically smooth or in transition stage or in a completely rough. So, now the equation 26 which we have derived here. So, here equation 26 can be written by substituting U star O. So, that we can write U x minus V divided by V square root of root f is equal to 2.03 log 10 y by r plus 1.32 as in equation number 29. So, again the measurement in pipe shows equation 29 to be adjusted, since generally what we theoretically or with respect to various expression we derive may not exactly match with what is the really we are getting in the experiments. So, it is seen that the expression which we are written here 29, we have to slightly adjust like this U x minus V divided by V square root of f, where V is the average velocity, that is equal to 2.15 log 10 y by r plus 1.43. So, this is with respect to measurement, this is the based upon some of the theory which we are developing here. So, this is the expression equation number 30. So, equation 30 gives the velocity distribution for various location pipe as a function of friction factor wherever the boundary be smooth or rough. So, this equation number 30 which we have written here. So, we can use it is for either a rough pipe or so, here this is an expression between the average velocity at any location and the friction factor. So, this expression we can use for smooth or rough pipe as a general tool. So, now equation 30 can be further written as, we can write this equation number 30 as U x by V is equal to square root of f 2.15 log 10 y by r plus 1.43 plus 1. We can simplify, and then at y is equal to r, the central line of the pipe, U x is equal to U max which gives the maximum velocity. So, U max by V is equal to square root of f 2.15 log 10 r by r plus 1.43 plus 1. So, this we can simplify as U max by V is equal to 1.43 square root of f plus 1 as in equation number 32. So, this expression is important, since this gives a relation between the maximum velocity for the average velocity and the friction factor of the pipe. So, for the turbulent flow in pipe, so this expression equation number 32 is an important expression where a relation between the U max V and friction factor f. So, now if you plot the velocity distribution for turbulent flow through rough pipe, you can see that the variation can be like this. So, this is the pipe which we consider, and here you can see this is the rough type pipe. So, you can see here initially the variation is say for the sub layer which we consider, the variation is like this, either it is we can assume as linear or we can approximate using the power law, and then after that laminar sub layer you can see that we will be approximating the expression with respect to the logarithmic law, or V is proportional to the average velocity, V is proportional to logarithm of y. So, this is the general pattern which is now we have shown through experiments as derived by Nikodas or through theoretical development or the various relationship. So, the laminar sub layer, it is the either we approximate as with respect to power law or with respect to the we consider as a linear variation in the laminar sub layer, and then beyond that we consider the variation with respect to the logarithmic law, or the variation is we are putting as the variation with respect to logarithmic variation. So, this both theoretically as well as experimentally we can show. So, now we will say, before closing this chapter on turbulent flow through pipes, we will discuss a small example with respect to the various relationship which we have derived here. So, the example is, say, here what we consider is as a small pipe in a 40 centimeter diameter pipe carrying water. Velocities were measured at the center and at a quarter point and were 2.425 meter per second and 2.275 meter per second. So, we have to calculate the discharge, the friction factor F, the shear velocity at pipe wall. So, here the data is given us, take the kinematic viscosity is 0.15 Stokes. So, for this problem, so here the pipe here. So, this is for turbulent flow in pipe. So, if this is the central line, so the diameter is 40 centimeter. So, the velocities were measured at the center points as, so here the velocity at the center point is 2.425 meter per second, and then at quarter point. So, here say this is r by 2. So, at this location the velocity was measured as 2.275 meter per second. So, this is the problem definition. So, now for this given condition we have to derive the, we have to get the discharge through the pipe, and then we have to determine the friction factor and the shear velocity at pipe wall. So, this is the problem. So, here to solve this problem we will use equation number 31. So, here the 31 is given here. So, here u x by v is equal to root of this expression we will use to solve this problem. So, if you, the equation is u x by v is equal to square root of f 2.15 log 10 y by r plus 1.43 plus 1 as given in equation number 1. So, now at y is equal to r, if we substitute, you can see that the velocity at the central line is given, the maximum velocity is given. So, if we put this expression 2.425 divided by v is equal to 1.43. So, here r by r. So, this expression goes. So, it is 1.43 root of plus 1. So, that is equation number 2. So, similar way the velocity at y is equal to point r is given. So, we can put this in this expression equation number 1. So, 2.275 by v is equal to 0.783 root of plus 1 after simplification and substitution of the values. So, now we got two equations with v and f. So, the unknown here are the mean velocity and the friction factor. So, we can solve for say either v or f. So, we get here after solving these two equations we can get v is equal to 2.093 meter per second and f is equal to 0.0123. So, now once we determine the velocity, average velocity, now v is calculated. So, we can easily determine the discharge. So, the discharge through the pipe, say once the average velocity is given, discharge is equal to q is equal to area of cross section multiplied by a into q is equal to a into v. So, here a is pi by 4 and d is 0.4. So, pi by 4 into 0.4 square into the velocity, average velocity v is 2.093 meter per second. So, from this we will get the discharge. So, the discharge is now 0.263 cumex. So, that we can calculate. So, now from equation 26 which we have already written here, equation 26 is here. So, this is equation number 26. So, if we use this equation number 26 here, we can write u x minus v by u star o is equal to 5.75 log 10 y by r plus 3.75. So, here for y is equal to r, we can write say ux will be, so that will be the maximum velocity. So, u max, this expression become u max minus v divided by u star o. So, this y by r is r by r, it will be 1. So, this will be cancelled. So, that is equal to 3.75. So, u max minus v by u star o is equal to 3.75. So, now say here we know u max is given us for this problem the 2.425, and also we have calculated v as v is calculated as 2.093 meter per second. So, that we can find out the shear velocity u star is equal to, say from this expression u star o is equal to 0.04 meter per second. So, like this we can solve various problems. So, what we have seen here so far is say for turbulent flow in say through pipes of say either say smooth pipes or hydrodynamically smooth or hydrodynamically rough pipe we are classified, and then for the hydrodynamically smooth and rough pipe we have derived the expression for velocity say at various locations or various depths. Say so basically you can see that in both cases either we are using the power law or the logarithmic law depending upon the Reynolds number and depending upon the whether the surface is smooth or the pipe is smooth or rough, and then we have derived various expressions for the velocity variation. So, also with this what we have derived the expressions we have verified with respect to the Nikoda's experiments. Nikoda's had conducted large number of experiments for various kinds of pipes, and then it is almost matching a slight small variations are there, otherwise the expressions which we are deriving is almost same. So, that way now the turbulent flow in pipe either smooth or rough we can utilize the expressions or the velocities equations based upon the power law and the logarithmic law. So, now to conclude this chapter, to summarize. So, so far in this chapter we were discussing about the laminar flow and turbulent flow. So, we have seen the various kinds of flow, types of flow, then we have seen how we classify according to the Reynolds number whether the flow is laminar or at transition or at turbulent condition. So, by Reynolds experiment and then using the Reynolds number, and then we have seen say with respect to this whether the flow is in the flow condition is between the laminar, transition or turbulent. So, according to that we have to see the condition, and then we will be generally deriving the equation. So, and then further we have seen say we are considered initially the laminar flow between. So, here this slide is summarizing this chapter here. So, for laminar flow between parallel plates we have seen we have derived various expression for flow between two fixed plates in laminar condition, and then one plate is moving, that condition Q-tape flow, and then we have seen flow between two parallel plates both are moving in the opposite direction. So, we have derived the expressions, generally the laminar flow expressions we have derived based upon the Newton's second law and then various other theories, and then we considered the laminar flow in pipes. So, there we have seen very similar way by using the Newton's law. There also for laminar flow in pipes also we have derived the various expression for the velocity variation, and then the average velocity expression for discharge, expression for the pressure variation, all this we have derived for laminar flow in pipes. And then we discussed in this chapter the turbulent flow. So, turbulent flow starting from the basic theory by considering the Reynolds equation, we have derived the basic equation for turbulent flow, and then say the Navier-Stokes form of the turbulent flow equation we have seen, and then we have discussed the various turbulent flow models, including zero equation model, then LES model, then one equation model, two equation model, like that for turbulent flow we have seen. Then finally, in this chapter we have derived say with respect to zero equation model, since as we have seen the turbulent flow is very complex, very difficult to determine the various parameters like velocity or the pressure variation. So, to explain further the turbulent phenomena, we have used the zero equation models or Prandtl's mixing length hypothesis, Karman's approach, and then for turbulent flow or flat plate or the parallel flow case, and then the turbulent flow through smooth as well as rough pipes. We have used this zero equation models based upon the Prandtl's mixing length theories, and then we tried to derive some expressions for the velocity variations. So, the importance of this, even though this equation based upon the Prandtl's mixing length theory is not 100% accurate, there are accuracy is less compared to the Reynolds equation if you use Reynolds and Navier-Stokes equation, but still this equation, these expressions gives say shows how the variation takes place, and it brings out the expressions, bring out the physics of the problem, how the variations with respect to turbulence, since the turbulent phenomena is very difficult to say quantify or very difficult to explain. So, these expressions based upon the power law and logarithmic law for turbulent flow in pipes or flow over flat plate, this expression can be used for the to see how the turbulent phenomena, and here we have tried to quantify based upon these expressions. So, these are the topics which we have covered in this chapter. So, further we will be discussing the various other chapters on the fluid mechanics.